The largest snake alive today, the green anaconda, reaches about 30 feet. It is already considered one of the most formidable predators in its ecosystem. Titanoboa was 42 feet, and the anaconda would have been its prey. 42 feet long, over a ton in weight, wide enough that a full-grown human could not reach around its body. It did not chase prey. It waited, submerged, still. And when something came within range, the outcome was already decided. The dinosaurs had been gone for 5 million years. Mammals existed, but most weighed under 10 pounds. The apex position belongs to reptiles, and Titanoboa held it completely. Everything in that ecosystem, what it ate, where it moved, how it evolved, organized itself around one animal. This is what Titanoboa did to its world. To understand Titanoboa's position, the post-extinction landscape needs context. 60 million years ago, the mass extinction event that ended the Cretaceous had cleared the largest animals from the planet. The dominant megafauna were gone. What remained was a world with open ecological space, and the competition to fill it. Mammals were present but small. Most were rodent-sized. The warm-blooded lineages that would eventually produce large predators hadn't developed them yet. That left reptiles. In the tropical swamps of what is now the Titanoboa Formation in northeastern Colombia, the ecosystem that filled the vacuum was not mammal-dominated. It was built around large reptiles, crocodilians reaching 20 feet, turtles with shells over 5 feet wide, and fish populations dense enough to sustain predators of significant size. Into this ecosystem, Titanoboa fit not as an invader, but as a product. The conditions built it. Titanoboa's size is not coincidental. Snakes are ectotherms, cold-blooded animals whose metabolic rate is directly constrained by ambient temperature. A snake in a cooler environment processes food slowly, grows slowly, and reaches a limited maximum size. A snake in a consistently hot environment can sustain a faster metabolism, digest larger meals, and grow larger across a longer lifespan. Paleocene Colombia was estimated to average between 30 and 34 degrees Celsius daily, consistently, without the seasonal variation that characterizes modern tropics. That sustained heat is what made Titanoboa physically possible. When researchers first recovered its vertebrae from the Titanoboa coal mine in 2009, initially mistaken for crocodile bones, they used its size to reverse engineer the climate. The logic runs in both directions. The climate produced the snake, and the snake's dimensions tell us what the climate was. Titanoboa became, functionally, a biological thermometer for the Paleocene. No modern environment is warm enough to produce it again. The modern tropics fall short of the sustained heat levels required. Every large ectotherm lineage, giant crocodilians, oversized turtles, massive snakes, has contracted in size as global temperatures cooled across millions of years. Titanoboa represents the ceiling of what reptile biology can produce under optimal thermal conditions. Those conditions no longer exist. 28 individual Titanoboa fossils have been identified from the Titanoboa Formation, enough to reconstruct its dimensions with reasonable accuracy. Length estimates center around 13 meters, with some specimens suggesting up to 14.3 meters. Weight estimates exceed 1,135 kilograms. Its vertebrae were nearly twice the diameter of a modern anaconda's. It was not venomous. It killed by constriction, wrapping its body around prey and applying pressure estimated at over 400 pounds per square inch, enough to collapse a rib cage, enough to stop circulation, enough to kill a large crocodilian. Analysis of skull fossils revised earlier assumptions about its diet. Initial reconstructions suggested a generalist predator targeting large prey. Skull morphology pointed more specifically toward fish, particularly lungfish, which were abundant in Paleocene swamps, as a primary food source. Crocodilians, turtles, and other large vertebrates were likely taken as well, particularly by larger adults. It was not a pursuit predator. Its mass made sustained active hunting inefficient. The behavioral model that fits best is ambush, lying submerged or concealed in shallow water, waiting for prey to enter range, then striking and constricting before the animal could respond. Escape from a full constriction was not a realistic outcome for its prey. An apex predator of Titanoboa's scale does not simply occupy the top of a food web. It organizes the levels below it. Crocodilians shared the Cerrejón environment with Titanoboa. They occupied overlapping habitat, the same rivers, the same swamps, the same prey base. That overlap means direct competition, and direct competition at that scale produces pressure. Crocodilian species in the formation show body sizes and behavioral profiles consistent with coexisting alongside a dominant constrictor predator. Whether through avoidance, niche partitioning, or direct predation of smaller individuals, the crocodilian population was not operating independently of Titanoboa's presence. Turtle species in the formation reached extraordinary sizes. Carbonemys coffrinii had a shell over 1.75 meters long. Large shell size is a defensive adaptation. The presence of a predator capable of handling large prey creates selective pressure toward better protection. The turtles that survived were the ones with shells Titanoboa found less efficient to process. Fish populations, the probable dietary staple, were regulated by consistent predation pressure from above. The abundance that made Titanoboa's population viable was itself shaped by the rate at which it consumed. The food web was not simply a hierarchy with Titanoboa at the top. It was structured around Titanoboa at the top. Here is the vulnerability concealed in size. Titanoboa's existence depended entirely on the climate staying stable. As an ectotherm, it had no internal mechanism to compensate for falling temperatures. Its metabolism, digestion, hunting efficiency, and reproductive capacity were all functions of ambient heat. Drop the average temperature meaningfully, and each of those functions degrades. Cooling doesn't just make a large ectotherm uncomfortable, it makes the biology progressively non-viable. Around 58 million years ago, tectonic shifts began disrupting ocean currents. Average temperatures started declining. The sustained, stable heat that the Paleocene tropics had maintained began to give way. For Titanoboa, there was no adaptation available. Warm-blooded mammals, which had been ecologically marginal during Titanoboa's dominance, were not constrained by ambient temperature the same way. As conditions cooled, they became more competitive. The thermal advantage that reptiles had held in the Paleocene heat began to erode. Titanoboa could not adjust its biology to a cooler world. The cooler world replaced it. The Cerrejón Formation preserved Titanoboa's world with unusual completeness. 28 individuals, multiple species of contemporaneous crocodilians and turtles, plant fossils indicating dense tropical vegetation, enough material to reconstruct not just the animal, but the ecosystem it occupied. Before this discovery, paleontologists placed the evolution of giant snake body sizes much later in the fossil record. Titanoboa pushed that timeline back significantly and demonstrated that extreme ectotherm size was achievable immediately after the Cretaceous extinction, given the right thermal conditions. It also clarified the relationship between climate and body size in cold-blooded lineages in a way that living species alone cannot demonstrate. Living snakes exist in a world that is too cool to reach Titanoboa's dimensions. The fossil record provides the data point that the living world no longer can. The disappearance and what it left. When Titanoboa's lineage disappeared, the Cerrejón ecosystem lost its organizing predator. Crocodilians that had coexisted with and been regulated by a dominant constrictor were no longer operating under the same constraints. Prey populations that had been continuously managed by Titanoboa's predation pressure faced a different set of conditions. The selective pressures that had driven defensive adaptations in turtle and crocodilian species shifted. The ecosystem did not collapse, it reorganized. What filled the apex position changed as mammals grew larger and the thermal advantage that had sustained giant reptiles declined. The Eocene that followed the Paleocene produced a different ecological architecture, one increasingly built around warm-blooded predators rather than cold-blooded giants. Titanoboa's disappearance was not an isolated extinction event. It was part of a planetary thermal shift that restructured which body plans were viable at the top of food chains. The climate that built it withdrew, and the animal built for that climate had no path forward. The Cerrejón coal mine in Colombia still produces fossils. The vertebrae are unmistakable, nearly twice the diameter of anything alive today. Each one is a data point from a world warm enough to produce something that the modern planet cannot. Titanoboa is not a curiosity from deep time. It is evidence of what stable, sustained heat does to the upper limits of animal biology, and what happens to those limits when the heat is removed.